continued on the classification topic. This slide talks about the model assessment. So once we train a classification model, just like logistic regression model, then we should be able to understand how how good that trained model is. So that is model assessment, and actually the way of validating the trained model is very simple. I briefly showed how to do that using the R software in the previous class. What we do is, in fact, we are making this kind of matrix, which is called confusion matrix. So in general, there are J number of classes, and using a training set, we train a classification model. So we have a data set, and there are multiple independent variables, and here we have a class variable. Then after training a classification model, we can get a predicted class, which is, let us say that this is y hat. And by comparing these two columns, we can make this confusion matrix where this C sub ij is the number of I class objects predicted as J class. So actually you can change the rows and columns, but in this slide, the rows indicate true class, so this is true. And the columns indicate the predicted classes. Then this C11, for example, indicates the class 1 objects that are correctly classified as class 1. And what about this one? This one is the class 1 objects, because the row indicates true class 1 objects that are incorrectly classified as class 2, right? Just like that. So all those diagonal elements are the number of objects that are correctly classified, and all these off-diagonal elements that are number of objects that are incorrectly classified. Okay, so the accuracy of a classifier is computed by this formula, by summing up all those diagonal elements divided by the total number of observation. We can get the accuracy. Then on the other hand, the misclassification rate or error rate is computed by 1 minus accuracy. That is equivalent to this formula. So we add all those off-diagonal elements, elements divided by total number of observation, then that becomes misclassification rate. So that is equivalent to this formula, right? Where the n is the total number of observation. So for example, in binary logistic regression example, here we have a class variable and 3 independent variables. And let us say that we train a logistic regression based on this data set, and we found the regression coefficient beta 0, beta 1, beta 2, and beta 3. Then by plugging in, for example, for the first observation, we plug in 0, 0 here, and 8 here, and 2 here. Then we're gonna get the logit p value, which is 0. Which is 2.08 something. So logit p is in fact log of p over 1 minus p is 2.80860, right? Then the p is in fact, by taking the exponential on both sides, what is that? The p over 1 minus p is exponential 2.0860, then p equals to 1 minus p times exponential 2.086, and then it becomes, what is that? The p1 plus exponential 2.086 equals to exponential 2.086 A6, is that right? Okay, so P equals to 1 plus exponential 2.086 and exponential 2.086. That is this one, it is 0.8895, right? Then based on the classification rule of logistic regression, if this predicted value is greater than or equal to, well, actually greater than, sometimes we use greater than or equal to 0.5, then we predict as class 1, right? Because we define this P as the probability that Y becomes 1. So its predicted class becomes 1. Just like this, we can make the predicted class, the logistic value and the probability that Y becomes 1, and predicted class by this classification rule, we can make this predicted column. And here we have true Y values. And by counting the case where we have one on true class and one on predicted class, we count this case. So here we have the case, such case here, and this one, right? And this one, and this one, this one. 4 cases. So there are 4 observations for one class objects that are correctly classified. Just like this, we can count the number of objects, 0 class objects that are correctly classified. In this example, which is 8, and incorrect classified objects and incorrect classified objects. So total number of observation is the summation of all those 4 numbers. Then the accuracy is the summation of the diagonal elements divided by total number of observations. So its accuracy is 0.8, and the misclassification rate is the sum of the off diagonal elements, which is 3, divided by total number of observations. That becomes 0.2. Okay, so we can see that if we train a logistic regression model based on this training set, then we can see that that logistic regression is about 80% reliable. We can believe that classification model with 80% accuracy. Okay, this is the way of evaluate. This is the way to validate the trained classifier. Isn't it simple? Yeah, pretty simple. So but the thing is that sometimes we have to, because sometimes this trained classifier is good for only training set, but actually we use this trained classifier for a new data set, so we should know how good that classifier is for a new data set. So what we usually do, I already talked about this at the first session of this class. What we usually do is once we have this a whole data set, then we divide that data set into 2 parts, training set and test sets. And we do not use this test set for training a classifier, for example, for training a logistic regression model. We use only this training set. Okay, then once we have this classifier, which is fx equals to fx, then there must be a y column here. Then we apply those x values here, and then we're going to get the predicted class. And just like the example that I showed you just before, we compare the true class with predicted class, and then count the number of incorrectly classified objects. Actually here the I is an indicator function that returns 1 if the condition in the parentheses is true. So if the predicted class is different from the actual class, it returns 1 for ith object, and we add up all those things, then what is this? Is the total number of incorrectly classified objects, total number of misclassified objects, and divided that value by the number of training set objects, the number of objects in the training set, then we can find the training error. This is called training error or training misclassification rate. And for the test set, we also have the true class label, and we apply this part. We apply this part to this fx, and then we're gonna get another column which is predicted class for the test set. And by comparing these two columns, we can get this test error in the same way. Okay, by comparing the true class label and predicted class label. This is the way of training and testing a classifier. Okay, isn't it very simple? So based on the previous example, what we do is we divide that 15 data points into two parts, and then training set has two parts where the training set has 1, 2, 3, 4, 5, 6, 7, 8 observation, and 1, 2, 3, 4, 5, 6, 7. Yes, 7 observation for test set. Actually, the amount for training set and the amount of the number of observations for test set, you can decide that numbers. But usually what we do is so usually what we do is 55 to 5 or 7 to 3 or 8 to 2. Actually, that is on your choice. Here, this part is training to test. You can use anything, actually, 5 to 5, 7 to 3, 8 to 2. But what you have to do is you have to randomly divide the data set into training and test. So just like this. Not the first 8 objects. You just randomly pick up 8 objects from the training set, and the other remaining observations will belong to the test set. Okay, after that, we use these parts only. We do not use this part for training a classifier, for training a logistic regression model, because the data set for training is different from this example. Actually, we used 15 objects, all of the 15 objects to get to get to get this logistic regression model. But in this example, we just used 8 observations, so the estimated coefficients are different from those that we obtained before. And then we put these x values and these x values into the model, right? Then we're gonna get this predicted class in the same way as the way that I showed it just before, and then we're gonna get the predicted class. I'm sorry, that was a probability that y becomes 1, and we're gonna get these predicted classes and compare the true class with predicted class, and we can get the training error or training accuracy, and by comparing these two columns, this column and this column, we can get the test errors or test accuracy by making these two confusion matrix. The first one is for training and second one is testing. So the accuracy is for training set is 0.75%. The accuracy for the test set is 0.71. So from these two results, we can notice that okay, the logistic regression method can return about 70 to 75, 70 to 75 accuracy. We can believe that model in that reliability, in that accuracy. Okay, we can believe that model with this confidence. Yes. So this slide, from this slide, actually it explains about then how we split the data into two parts, training and test. And I said that we have to divide the data set randomly, but sometimes the number of observations of class 1 and the number of observations of class 0, they could be quite different. I mean, the distribution of class 1 and distribution of class 0 could be quite different. So then in that case, we have to split the data set very carefully. And I'm going to explain using this breast cancer data set. And that was actually obtained from the University of Wisconsin, I think, medicine hospitals from this guy, Dr. William Ulfberg. Ulfberg, yes, Dr. William collected this data set at this year. And did I show you this data set before when I was explaining about the concept of classification? Yes, I think I already showed that. And there are 9 independent variables and 1 class variable, and the class values are benign and malignant and all those numeric independent variables. Actually, the data set looks like this one, and I uploaded this data set onto iCampus, so you can download from the iCampus. Let me go to the iCampus. So this is the class material, and then click this one. Then you're gonna see the class materials that I uploaded, and then if you click this model assessment, then there is a link to a data set which is cancer.csv. By clicking this one, you can download this data set. And yes, there are, here is the first column is the class variable and the other is independent variable. Okay, and there are, how many observations are there? 683 observations are there. And the thing is that in this data set, there are 444 benign observations and 239 malignant observations. So this is not 50 to 50. The distribution of class variable is lightly skewed to this class, right? This class observation, the number of observations in this class are more than number of observations of this class. So by running this command read.csv, you can read the external CSV file into R session, and then using this table function, you can see the number of observations on each classes. Then in this case, if we do just randomly split into training and test, the probability, actually the chance to pick up the benign observation is higher than the chance to pick up malignant observation. So we may not be able to preserve this distribution in training or test. So in this case, this case is actually called, imbalanced data or imbalanced class. And the classification for this imbalanced data is called imbalanced data classification. This is one of the most important one of the most important topics in classification area, because in fact almost always there are many cases that the class distribution is imbalanced. Let me talk about this imbalanced data classification later in more detail. But in this case, to split a data set into training and test set, what we have to do is something called stratified random partitioning. Stratified random partitioning. So the breast cancer data set, this data set, has more benign observations, need to pay more attention when preparing training and test data sets. And we have to preserve the original class distribution by this code. We can do that. Then actually the idea is So in our breast cancer data set, we have Y class, and we know that there are more benign and less malignant. Then what we're going to do is actually we split the data into two parts, benign data set. So this data set contains only benign observation, and malignant data set. So this data set contains only malignant data set. And we randomly divide this benign data set into two parts, training and test. So let us assume that we want to divide into two parts by this ratio, 7 to 3, 7 for training and 3 for test. Then we randomly divide into two parts for training and for testing. Okay, and in the same way, we divide into two parts so that the ratio becomes 7 to 3, 7 to 3. And concatenate these two parts into training set and concatenate, add those two parts for as a training set, right? Then here we have both benign observation and malignant observation, benign observation, malignant observation, and benign observation. Do you understand this way? Okay, then the ratio becomes 7 to 3. This is not just assumption. Okay, this whole procedure, this procedure is called stratified random partitioning, and this R code does that. And let me show that. Let me run this code in R session and launch R software, and then let me specify the working directory, which is data mining, folder on the desktop. And actually this folder has the cancer dataset here. So let me just copy and paste the whole commands to this editor. And first I have to read that external CSV file into R. D.c read.csv cancer.csv, and because the first row is the column name, header equals to true, and the data is separated by comma. Okay, on the first line, then we read that cancer data set into R session. Okay, and then what this second line does is we just subset the benign data set by this comparison operator, right? If that y value is benign, then it returns true, and if not, it returns false, and then we're gonna get the indexes of true, and then so this part is just the selection of the benign observation, and we store that into d.c.ben, and in the same way we are making d.c.mal for malignant dataset, right? So these two lines is to split into benign dataset and malignant dataset, and to make the random splitting of training and test, what these four lines does, it's just shuffling rows. So this command, what is this? Is to figure out the number of rows of benign dataset, is to figure out the number of rows of malignant dataset. So just run these two lines. Then this nr.ben has 444 and nr.mal has 239. Okay, and then what is this sample function does? Let me run just this part. Then it's just random imputation. I'm sorry, not invitation, random permutation of the numbers from 1 to what? 1 to 444. So it's just randomly shuffling the rows of benign data set, and this part is to randomly shuffling the malignant data set. Okay, then low numbers are, you can see that the low here, the low numbers are commingled, right? And then what you're gonna do is we're gonna split the benign data set into two parts, training and test, and then this command is to do that, and we're gonna split the malignant data set into two parts, into training and test, by taking first 70% of the rows, okay, from 1 to, what is this one, nr.band times 1.7, because I want to split that data set into training and test with the 3 7 to 3 ratio. So this one is this part, and our dot band times 0.7 is 310.8. So by just taking round function, I'm gonna get rounded number, and by this one, what is that? What does this line does is taking the first 70 rows of the benign data set, and I'm gonna store that into this name, d.c.band.train. Then this part from the line right after this, actually this one is 311. So from, I'm gonna take the 312th data set, 312th observation to the end of the rows. I'm gonna make it as a test set for benign data set. Okay, I think you can understand what these two lines do. So it's splitting into two parts, training and test for benign data set. These two lines do the same thing for the malignant data set. Then by using this rbind function, I'm gonna concatenate this d.c.band.train, d.c.mal train. Okay, and I'm gonna do the same thing. I'm gonna do the same thing for the test set. Now it's done. Actually, that's everything about the stratified random partitioning. Random, randomness is here, and stratified partitioning is here. Okay. Then now take a look at the distribution of training set. The class distribution of training set. There are 311 benign and 167 malignant, and in test set 133 benign and 72 malignant. So the distribution of this class distribution is preserved in both training set and test set. Okay, so now you understand what is the stratified random partitioning. Okay, then now you can see that for training set, the class distribution is same with the test set. The class distribution is same. Then using GLM function, I'm gonna fit a binary logistic regression model. The data set is d.c.train, which means that I'm gonna use training set only to train a logistic regression model. And here, this one is formula. I explained already about this one when I was talking about the logistic regression. This formula means that in this data set, y is class variable, and the other columns, this dot indicates that the other columns are set to independent variables. And then the family is binomial, and which option is logit, which means that I'm gonna fit a binary logistic regression model. And using this summary command, we're gonna be able to see, we can see that beta 0 and beta 1, beta 2, beta 9. Okay, we can see the estimated regression coefficients. Then, and I already showed you that we can use the predict function to make a predicted class. And the first input argument is predict trained classifier using R software using GLM function. And the new data is d.c.train, which means that I'm going to still put the x values of training set into this model to make a prediction. And if you specify this third input argument, which is type equals to response, then you're going to get the probability that becomes class 1. If you cancel this third argument, then this predict function returns what? Logit value. You saw that before when I was showing you the example of logistic regression in logistic session. Okay, so by doing that, by learning from here to here, you're gonna get the predicted probability that class variable becomes 1, right? Because the classification rule is we assign an object into class 1 if the predicted probability is less than or greater than or I'm sorry, not less than, greater than or equal to 0.5. We predict that observation into class 1, so we use round function to make a predicted class. Okay, so I have to show you that using, okay, let me do that. Let me train a classification model using this command. GLM function first. Paste the command here, and then copy and paste this part. And copy and paste this part as well. Let me copy all these things. Oops. Because these are the results, let me erase this part. Okay, so using just GLM function, I fit a logistic regression model, and using this summary function, you can see this estimated regression coefficient, and using predict function, you're gonna get the predicted probability that y becomes 1, and using this round function, you're gonna get the predicted class 0 or 1, right? And then that, actually, I did for the test set. Actually, I should have done that for the training set first. And then using, what is this one? d.c.train at y. Is this one true class? This one is true class, and this one is predicted class. So using these two columns, using the table function, we can get this confusion matrix. Okay, so the rows are true and columns are predicted. There are 304 observations, class 0, benign objects that are correctly classified, and only 13 objects were misclassified for training set. Then we want to know that if this goodness is still valid for test set, for the new data set. So what we're going to do is we're going to make a prediction for the test set that was not used to train a classifier. So by learning this command, we can get the predicted class for the test set. Here, this one is the predicted class for the test set, and we can make a confusion matrix by the same way. And we can see that there are 12 observations are misclassified, and 62 malignant observations are correctly classified, and 131 benign objects were correctly classified. And actually, these two lines is to compute the accuracy for training, and actually this should be test. So this is confusion. This cm.train is confusion matrix for training set, and this cm.test is the confidence matrix for test set. And what does this command, this diag function does is it extracts the diagonal elements only from a square matrix and then making sum. This what this command does is we make a sum on the diagonal elements of this confusion matrix for training set, and then that is divided by total number of observation, then that is the training accuracy, which is which is 97%, so about 97%. And we can get the test accuracy in the same way, and its accuracy is 94%. And to believe a classifier, to believe trained classifier, what is the most desirable is that those two measures, training accuracy and training accuracy and test accuracy, they should be similar values, right? Then we can believe that the trained classifier. If this value is too good and this value is not that good compared with the training accuracy, then we say that classifier is overfitted. It's like we say that, for example, training accuracy is 99%, but test accuracy is, for example, 60%. There are a huge gap between these two values. Then a trained classifier is just good for training set, and this situation is called overfitted to training set. It's so we cannot actually use this classifier for testing a new data set because the test accuracy is not good. So we actually the over this is called overfitting problem. And just for information, we should avoid from this problem. Then the way of avoiding from this problem is that is case by case method, technique by technique. So I'm not going to talk about this for now. And actually, what I explained just before is about dividing a data set into training and test, but we can repeat this training and test several times by Bruford cross validation method, by something which is called Bruford cross validation. What we do to this one is the given data is divided into Bruford. V could be actually the V is your choice. It's up to you. The choice of V is up to you. So you can divide a data set into 5 folds. You can divide a data set into 10 folds or 15 folds, 20 folds. It's just up to you. So you choose this number, 3 folds. Or sometimes it's called n-fold cross validation in other literature, and sometimes it is called, I guess, k-fold cross validation, something like this. So here V again is of your choice, and in this cross validation, what we do is we divide into V-fold and then we train a model using the first v minus 1 folds to train a model, and we use the remaining fold for testing. Okay, or even this way is okay. We use the first fold as a test set and the other fold as training set, and we change the testing role one by one. So at first this one is test set. In second experiment, this D2 is used for training set, and the first fold and the other folds are used for training. So we just change as the role of testing, the role of test set. At the first time we do testing with this one. In the second time we do the testing using this set and using this set. Then we can do training and test v times, right? So this figure shows that, and we can average the test error over the v fold, right? This is just one case. So learn model using this fold and use this to get test error. And so this R test FV is this one is predicted class of with classifier, and if that is different from true class, then we can compute the test error for the with model. Okay, and then we can calculate this test error for across the all of the predicted models. Then by averaging those test errors, we can get cross-validated error rates of a classifier, of a classification model, which is, for example, logistic regression. Logistic regression or decision tree that we're gonna take a look at, or support vector machine. No, we don't take a look at, we don't learn about support vector machine. Neural network. We can employ different classification methods to build a classification model, and then by comparing this cross-validated error rates, which method is good for my data set. Actually, there is no always outperforming classification technique for every data set. So what we usually do whenever we analyze a data set, whenever we train a classifier, we apply all of the classification techniques that we know to the data set we have, and then we select the best one sometimes by the cross validation. Okay, that is called cross validation. So instead of doing training and test just once, we do that v times, okay, and we get the averaged test error. That is the cross validation, and that's everything for model assessment, and this is what we usually do to assess the goodness of the classification model. Okay, thank you for your attention.